Now welcome to this lecture, which covers some basics of path planning, and you will learn about the algorithms of Dijkstra, A-star, and finally a path planner that does trajectories which can be driven by a real car. So before we start, let me show you some of the results. So there's a graphical user interface where you can explore the results of all your algorithms, and this allows you to set a start node, an end node, and then watch how the algorithm finds the path from start to the end. And you may of course change start or end nodes, and you can draw interactively obstacles. So the path has to go around those obstacles, and as the path length increases, you will see that the number of nodes that are visited also increase. So this is Dijkstra's algorithm, and we will develop this first, and then we will modify this to obtain the A-star algorithm, where fewer nodes are explored. So in general, the search space is smaller, and it is so fast that you can build up and solve complicated mazes at interactive speeds. Finally, we will use a potential function to keep away the path from obstacles or to find your path in really cluttered environments in such a manner that it goes between the objects and not along the edges of the objects. And finally, we'll come up with a path planning algorithm which plans trajectories in such a way that a car which can go straight or make a left or right turn with a certain minimum turn radius can actually drive those paths. And we will see how this algorithm is pretty creative in finding alternative ways in case there's obstacles preventing a given maneuver. We'll also allow it to go forward and backward, and as we will see, it is then able to make pretty complicated maneuvers. And those maneuvers are not very much different from what we would do if we encounter a narrow blocked road ahead and probably have enough space to turn the car at a nearby parking lot, or if this is not possible, if we can go forward and backward even with a car right behind us. So let's first have a look at the algorithm of Dijkstra, which is named after the famous Dutch computer scientist Edsger Dijkstra. Now suppose we have a graph consisting of nodes and edges, and we want to find a path from start to goal with a minimum length. Now say, considering the length, we assume that the edges of the graph are annotated with costs, such that, for example, this edge might have a cost of 40, this one a cost of 50, and this one a cost of 20. And all the other edges have associated costs as well. These edges may be directed or undirected. For the moment, you may assume that this is a kind of a road network where the nodes are intersections and the edges are road segments connecting the intersections, and the annotated costs are the distances between intersections or the time required to travel between two intersections, or some mixture of both. Now the task is to get from start to the goal with minimum cost. We know that the cost of going from start to start is 0. So the cost of reaching the start node is 0. Now what is the cost of reaching the goal node? Well, in order to reach the goal from the start, we have to pick a path through the graph. Now which edge should we pick first? Well, and intuitively, we should pick the edge with the lowest cost first, being this one. And since the edge cost is 20, we reach this node with a cost of 20. Now we know the final cost of reaching start is 0, and the final cost of reaching this node is 20. Why do we know this? Because say there would be any alternative path in the graph, which we may detect later on, then the cost of this alternative path will not be smaller than 20. How can I know this? Well, because the first edge in this path already has a cost of 40. And now you will notice this argument only holds if negative edge costs are not allowed. So for example, if it would be allowed that this edge cost is minus 10, this is also minus 10, this is also minus 10, and this is minus 5, then the total cost along this path would be 40, 30, 20, 10, 5. So it would be possible to discover a path later on with a smaller cost than 20. But if negative edge weights are not allowed, then the total cost along this path would be larger or equal to 40. And so the trick is, once we pick this node here, which has the minimum cost among all nodes that I can reach from start, I know its final cost. And so I have never to look again at the cost of this node. Since this is the case, I can imagine the following. In the beginning, I have a set of nodes which I have visited. And this set contains, in the beginning, just the start node. Also, I know the distance to the start node is 0. So this set is not only my visited set, it's also the set which I know being optimal. Now searching for the node which can be reached from the optimal set and has smallest cost, I obtain this node here. And once I pick it, I know it will be optimal too. It cannot change its cost later on. So my optimal set just gets larger and also contains this node. Now in general, the situation at an arbitrary point in algorithm execution is as follows. There's a visited set and the start node is part of that visited set, and I have already added 0 or more other nodes to this visited set. So all those nodes which I have added already are already assigned their optimal distances. Now some of those nodes may have outside connections. That is, there's a direct edge from those nodes which are in the visited set to other nodes which are not in the visited set. Now since I know the cost of all those nodes, and I also know the cost associated with the direct edge to a node outside of the visited set, I can also compute the cost of those nodes that can be reached by a direct edge from a node in the visited set. Now what happens next is exactly the same as what we did in the case where our visited set consisted of only the start node. We will look among all the nodes that can be reached from any node in the visited set for the node with the minimum cost, and we will add this node to the set of visited nodes. Then the following will happen. First of all, we know the final cost of this node is indeed 100. Second, we will have to look at all the neighbors of this node, because it may be the case that now we find nodes that can now be reached from our new enlarged visited set by a direct edge. For example, in this case, the cost of this node is 100 and the cost of the edge is 10. So this node, which couldn't be reached by a direct edge previously, can now be reached with a cost of 110. But we have another important case too. So this node that was previously reached with a cost of 200 can now be reached via the newly added node over this edge with a cost of 30, making a total of 130. So we have two important cases here. The first one is the case where we discover a new node which was not previously connected to our visited set, and so we change its cost from infinity to 110. In the other case, we have found this node earlier, and we determined that we can reach this node from within the visited set using this edge with a cost of 200. But then this node doesn't get picked right away, and so while other nodes are being inserted into the visited set, we may discover that the distance gets smaller until at some point the node is picked and also added to the visited set. So keep in mind those two cases. Discover a node for the first time and decrement the cost of a node that has been discovered earlier but which has not been added to the visited set already. Now if we look at how the algorithm proceeds, we find that there are actually three sets involved. So we first have the visited set, which contains all nodes for which we know the correct final cost already, And we have another set, which is kind of unknown, consisting of all the nodes which we did not reach so far. And we have this set in the middle, which is the search front of our algorithm. And for all nodes in this set, we already know their cost. However, it is not necessarily the final cost, which is only fixed when a node is taken from front and added to visited. Now, keeping the nodes in two separate sets, visited and front, makes a lot of sense because the search for a node with minimum cost only happens in the search front set. So we neither have to look at the nodes that are in visited already, nor do we have to look at the nodes which are unknown. Now let's write down this algorithm, and I will do so in a quite informal way to keep it simple. So we have a set called front, and initially this is just the start node. And then we iterate as long as there are elements in our front. We get the node n with minimum cost, where get means we pick the node in front and then we delete it from the front, and then we put it into our visited set. So we say mark the node n as visited. And now, as you remember, I have to update all the direct neighbors of n. So inside this while loop, there's a for loop for any direct neighbor m of n. So any direct neighbor of the node n which we picked. And it doesn't make sense to look into a node which has been visited already. So we make sure that m has not been visited so far. And for any such neighbor m, we have to add m to the front. And you remember, this was only the first case. If it is already part of the front, we have to check if it has now that we added n a lower cost. So either add or adjust the cost if m is already in front and its new cost is lower. So this is the algorithm due to Edsger-Dijkstra. Now let's make an example to see how this algorithm works. Say I have this simple graph consisting of 5 nodes, where this is my start node and this is my goal node, and these are the edges with associated costs of 1, 1, 4, 1, 2, and 4. So this is start, this is goal. Now how does the algorithm proceed? We have our set front, and in the beginning this contains only the start node. And since we also know the cost of the start node, I will add this to my one and only element in front. So this is the situation after initialization of the algorithm. Now comes my loop while the front is not empty. Well, it is not empty, so I pick the node with minimum cost from front, which is the only node with cost 0. So I pick it and I remove it from front. Then I put it into the set visited, which for the moment we will visualize by crossing out the node as being visited already. Now I'll have to do a loop over all direct neighbors of the node just added. So let's give them names. Now one direct neighbor is A. A can be reached at a cost of 1. Put that into front. Another direct neighbor is C, and it can be reached by a cost of 4. And there are no other direct neighbors. So we jump back to the beginning of the loop, select the element with minimum cost, which is node A. Mark A as visited, and by that very moment we also know the final cost of A, which is 1. Then check all direct neighbors which have not been visited yet. Well, one direct neighbor is S, but S is already crossed out because it is in the visited set. The other direct neighbor is B. So I can go to B, and what is the cost? Well, the cost of reaching A is 1, and the edge between A and B has a cost of 1, so the total cost is 1 plus 1, which is 2. And there are no other neighbors of A. So we jump back to the beginning of the loop and pick again the minimum element, which is B with a cost of 2. So we cross out B, and we check all neighbors that have not been visited yet. So A has been visited already, but G has not been visited yet. So the cost of B was 2. The edge between B and G is 4. So for a total cost of 6, we can visit G. The third neighbor of B is C. and C can be reached via this edge with a cost of 1. So B is a cost of 2. By the way, I should mark this here. The edge has a cost of 1, so I can reach C with a cost of 3. But C is already in the front, so what happens is that this entry in the front gets updated. And so we can reach C now with a cost of 3. Now we pick the next minimum element of front, which is C. So we cross it out, we know its final cost, and we check its neighbors which have not been marked yet. So the only neighbor that is left is G. Since C has a cost of 3 and the edge has a cost of 2, G can be reached by a cost of 5. So we see here again we update an element in front, and this is also the final element which gets picked in the last execution of the loop. So G is marked and can be reached with a final cost of 5. So if you now look at the optimal path, we can go up here for a cost of 1, down here, so the total cost is 2, 3, and 5. So this is the optimal path from start to goal. Whereas there's a number of other paths, for example 1, 2, 6, or 4, 6, or 4, 5, 9. And thus we can verify that indeed this path is the one with the lowest cost. Now in our programming exercises, we will actually use a slightly modified version of this algorithm, which is not more efficient, but it is easier to implement. So let me first write down our previous version. So, and as you remember, down here we had the alternative add m to the front or modify the cost of m if it is already an element of front and the new cost is lower. I want to get rid of this complicated part down here, so I'll just leave it away, meaning that if I added it to front already with a higher cost, and later I determine there's a different path to the node m with a lower cost, then I add it again to my front, and I think that doesn't do any harm, because then when I scan later through front, looking for the node with minimum cost, I will pick the element with a lower cost first. So, but now I have to be aware that after I pick this, there may be still other copies in front with higher cost. And so I can't be sure that a node can be only once in front. And so as a trade-off to the amount of work I have saved myself down here, I have to make sure up here that I handle each node only once. So I have to skip the further execution if node n, which I just picked, has been visited already. So this is a trade-off. Down here, I don't have to search if this element is already in front, and if so, if I have to modify its cost. But then up here, I have to add a line that prevents me from looking at nodes twice. So now let's have a look how the execution of this algorithm works on our previous graph. So again, this is our graph. This is our start, and this is the goal we want to reach. And it has those edges with costs 1, 1, 4, 1, 2, 4. How does our front look like? Well, again, we start with cost 0 and node S. We pick the minimum element in front, cross it out, and note the final cost. Then we check the direct neighbors, which is A with the cost of 1 and C with the cost of 4. We pick the minimum element, know its final cost, and check the neighbors of A, which have not been visited yet. S has been visited, B has not been visited yet and can be reached with a cost of 2. So far, our algorithm proceeds in exactly the same way as our previous version. Now let's have a look at B. That's the minimum cost element, cross it out, the cost is 2. We check the neighbors that have not been marked yet, which is G, which can be now reached with a cost of 6, and C, which can be reached with a cost of 3. Now here's the difference to our previous version. We now also enter this element into the front. So the next thing that happens is we pick the C, mark it as visited, and we know its final cost. We check all neighbors, and we find that G can be reached now with a cost of 5. Now we pick again the minimum element from the front, and we find C. Now here our additional line of code prevents us from checking the neighbors of C again, because as we see that C has been marked as visited already, we will skip the rest of the loop. So we will directly go back and pick the minimum element in front, which is now G with a cost of 5. So we will mark G as visited. We know the final cost, which is 5. We search all neighbors, but they are all marked as visited now. We go back to the top of the loop and we find there's still one element. We pick this, and again, we see as we marked G already, we will skip the rest of the loop, and our front is empty. So as you see, we arrived at the very same minimum cost of 5. However, we did not have to treat the case where a node is already in front and we have to find it in front and then check if its cost gets lower by the new path. So that makes it simpler. However, this comes at an extra price, and you see that a total of 7 elements were put into our front, whereas in the earlier version of our algorithm, we only put 5 elements in there. Namely, each node of the graph was put exactly once into front and was taken out exactly once from front.